Welcome to the session on AI security, where we will explore the attack surface of large language models and the expanding cybersecurity risks associated with them. In this video, we will break down what an attack surface is, how it applies to AI systems, and why LLMs have a broader attack surface than traditional IT applications. To begin, let's first understand where large language models fit in the AI ecosystem. Different AI models serve different purposes. For instance, computer vision models analyze images, speech models process audio, and recommendation systems predict user behavior. However, LLMs stand apart because they are designed to process human-like text dynamically and interact in real time. And unlike other AI models, LLMs have more directly exposed public-facing components because they have to process dynamic user input in real time, and this significantly increases their attack surface, making them more vulnerable when compared to other AI models. And to give you a structured understanding, I have broken this session into two key sections. First, we will start with understanding the concept of an attack surface, where we will define what an attack surface is and look at some practical examples such as laptops and web servers and see how their attack surface differs from each other and what are the components in them that increase or shrink their attack surface. Then in section 2, we will zoom into large language models, breaking down their key components and understanding their attack surfaces. We will then analyze how attackers target them and explore some real world risks associated with the LLMs in production. So by the end of this session, you will have a solid grasp of how attack surfaces work and why LLMs require a different security approach compared to traditional IT systems. Now let's begin our section 1, where we will break down the core idea of an attack surface and then explore some real world examples. So understanding this attack surface concept is very crucial because minimizing an attack surface is one of the key strategies in cybersecurity. So one really has to understand what an attack surface is in deep. So in simple terms, the attack surface of a system is determined by the number of components that are publicly exposed and accessible to potential attackers. The more public-facing components a system has, the larger its attack surface and the larger it has the risk of cyber threats. Now let's take an example here of two systems with the same number of components but different levels of exposure. The system on the left here, it represents an internal application within an organization where employees have to access this application while being inside an office or through a VPN. It is not exposed to the internet, meaning its attack surface remains small. The system on the right here, however, is an external facing application. It is such as a customer portal or a public facing API or a public facing website. And since some of the components like the web service, APIs, user interface, they are directly accessible from the internet, they open the entry doors for the attackers to come in through these open publicly exposed components. And this increases its attack surface significantly when compared to this internal system. So the key takeaway here is that it is not the total number of components in a system that define an attack surface, but how many of them are exposed publicly. And to give you a structured understanding, I have broken this session into two key sections. First, we will start with understanding the concept of an attack surface, where we will define what an attack surface is and look at some practical examples. Now let's take a practical look at how attack surfaces differ between two real-world systems, a work laptop and a web server. On the left here, we have a corporate work laptop. It is not directly exposed to the public internet. There is no open port or public-facing service. However, it still has an indirect attack surface. For example, a user might download a malicious email attachment, click on a phishing link, or get compromised through an internal network. That's why we label it as an indirect public exposure system. However, the attack surface here is much smaller because the components of this system are only internally accessible. all the connections are opened inside to outside. They originate first in the internal network and then go outside. Not like an externally exposed system where the connections can originate from outside first and then come inside. And on the right here, we have a web server. This server has public facing components. That's why I've made a red exclamation marking here. It has components such as open ports, web interfaces, and APIs, which can be accessed by anyone on the internet. These directly exposed components make its attack surface significantly larger than that of a laptop. Now let's look at what are the components in a work laptop that make up its attack surface. Unlike servers or web applications, a laptop does not have a direct public exposure, meaning it does not host any open services accessible from the internet. However, it still has an attack surface. It is still vulnerable to attacks. And on the broad level then, I am categorizing the three main attack vectors that introduce indirect public exposure to a laptop and can become the entry points for the attackers to come in and control the laptop, compromise the laptop. First is USB, second is internet, browsing and downloads, and third is email. While these are the three major points that I'm going to discuss here, there are many more attack vectors that exist, such as unpatched vulnerabilities, insider threats, weak remote access security. However, on a general level, to simplify and to help you understand what makes up the attack surface of a laptop, I'm showing you these three categories for your broad level understanding. So these are the three attack vectors, entry points for the attackers to come in. Attackers can come in through USB devices, wireless peripherals, external hard drives that can act as entry point for malware. An attacker can plant a malicious USB drive that automatically executes malware upon connection, leading to ransomware-like infections. Then internet and browsing downloads. When browsing the web, a user might accidentally click on a malicious link, leading to drive-by downloads where malware is installed without any user interaction. Users may download seemingly legitimate software that is actually a Trojan or contains a backdoor and end up compromising their system. Then email. Phishing remains one of the most effective ways to compromise a laptop and the most exploited attack vector. Malicious email containing links to fake login pages, stealing credentials, infected attachments. So attackers can use business email compromise technique to impersonate trusted sources and manipulate users. So these three components on a broad level, they come together to create the attack surface for a laptop. Even though these are not externally accessible, they are only internally accessible, they are still enough to create a attack surface for a laptop. Now let's take a look at a web server and analyze how its attack surface compares to that of a work laptop from the previous slide. So unlike a laptop which has primarily indirect public exposure, a web server is an externally facing system that directly exposes multiple components to the internet, and this makes it far more accessible to attackers and significantly increases its attack surface when compared to a laptop. Now, why is the attack surface of a web server much larger? Because publicly exposed entry points. A web server will typically have these open ports, APIs, login portals, other services that it is hosting. Attackers can directly interact with these services, attempting exploits like brute force attacks, API abuse, injection attacks. So public APIs often expose sensitive functionalities and they can be exploited through API scraping, data exfiltration, or API abuse attacks. Then a web server may be hosting some unpatched vulnerabilities that can allow attackers to exploit SQL injection based attacks or remote code execution attacks on the databases. Databases and backend systems that are connected to the server may also be targeted, even though they are not directly exposed. And then user authentication pages, user login interfaces, they can be targeted using credential stuffing, phishing, session hijacking. So overall, these exposed services, they increase the risk of breaches. And since a web server is always online and exposed, it is continuously scanned and targeted by bots and threat attackers looking for vulnerabilities. And therefore, the attack surface of a web server is much, much larger when you compare it with a laptop. With that, we conclude section 1. Now let's shift our focus to section 2, where we examine the attack surface of large language models. Before we dive into the attack surface of large language models, it is important first to understand their internal architecture. So, just like traditional IT systems, such as a web server that consists of key components like databases, APIs, and user interfaces, an LLM system is also made up of various interconnected components that work together to process user input and generate responses. However, a thing to note is that an LLM system is far more complex and expansive compared to a traditional web server because it includes additional layers such as model training, inference data, external APIs. So, because of this, the attack surface of an AI model is also much greater than a traditional IT system because it has more components, and plus it will have more components that will be exposed directly to the public. And the way these components work, that will also be very different. When you interact with a web server, it's a very controlled interaction, but when you interact with an AI system through a prompt, you are sending the data, and that unstructured data gets processed in the AI model directly, and then a response is generated. So you can the attack vector of prompt injection attacks, it increases very much in AI system when compared to other IT systems. So in this slide, we will break down the key components one by one. Let's start with prompt. This is the query or the instruction that is given by the user to the AI model. Example would be when you ask ChatGPT something, you are giving an input as the prompt to the AI model, and then AI model will process that input by using the LLM processing unit. What is the LLM processing unit? Now, this is the core engine that will handle the prompt processing, which will execute logic and manage instructions based on what AI model you have deployed. And the AI model component itself is your ChatGPT, your Llama, or Google Lambda that you have implemented, which will work in conjunction with the LLM processing unit. Now, LLM processing unit, it will also have these subcomponents: agents, serverless functions, API calls. What is an agent? These are specialized components that will handle specific tasks autonomously. For example, in ChatGPT, if you introduce a plugin that can fetch live data or maybe provide you with some stock updates by interacting with external tools, then it becomes then you are using and this agent as a submodule, this plugin as a submodule for your deployed AI model. Instead of agents, you can also do it through API calls. You can make some API calls, use some external APIs to achieve the same. So agents and API call, these are the components that act like a submodule. Then you have serverless functions. Serverless functions are on-demand execution functions, where a cloud-based function that executes some specific tasks on demand without needing a dedicated server. For example, in AWS, you have Lambda functions that are provided by AWS for doing some kind of automation. Another example would be if you have ChatGPT deployed in an Azure scenario, and your ChatGPT is using an Azure function to check for some weather updates on demand, then it is using a serverless function. You don't need a server for that kind of thing. And so that's about the LLM processing unit. It is like a processor that is working for your brain, your deployed AI model. Then you have training data. LLMs are trained using massive data sets from books, websites, code bases. So, when ChatGPT was developed, it was trained on publicly available internet text up to its cutoff date. So whatever training data you take for your AI model, that is, goes into that you can say forms the training data component. And I will discuss with you a very interesting example of training data poisoning attack on the next slide. Inference data, this is the data that is generated during live interaction between users and models. For example, if ChatGPT is fine-tuning its responses based on previous chat history, then it's interference data. That's interference data that it is using. It is the live interaction that is going on in the chat between the AI model and the user. Same way, external APIs we have already discussed in the API call update and query. This is the component where LLM can update or retrieve data from internal databases for context aware responses. For example, if an enterprise is using a ChatGPT enterprise version for storing some chat history for businesses, and based on that, if AI model has to respond to some future queries, it will store that. It will use those chats from the database as reference for context awareness. So in short, then, on this slide I'm showing you that an LLM system is not just a model generating text. It consists of it is not working in isolation. It consists of these multiple interconnected components that are handling this data flow, API interactions, user prompts, and storage mechanisms. So this multi-layered architecture significantly then increases the attack surface of an LLM system that we will see on the next slide. On this next slide, now we are transitioning from understanding LLM components to understanding their attack surface, meaning what are the attack vectors through which the attackers can come and compromise your AI model and your AI system. So this slide is highlighting some key attack vectors here that you can see, which are highly vulnerable when the LLMs are deployed in production. So unlike traditional IT systems, LLMs will interact dynamically with user input. They will process large amounts of data. They will have integration with external services, creating multiple entry points for potential exploitation. So we will study these attack vectors, discuss them one by one. First attack vector we can take is the user prompt. So in user prompt, the attack vector would be the prompt injection attacks, where a malicious user can craft some malicious input to manipulate your AI model, to bypass some safety filters, to make the model generate unintended responses, or to extract some sensitive information. An example of this, if I have to give you, is the Chevrolet Tahoe chatbot incident, where last year a chatbot deployed by a Chevrolet dealership was manipulated through prompt injection, causing it to offer a Chevrolet SUV for just $1. Now, obviously, the chatbot was not legally authorized to make such deals, and Chevrolet was not obliged to honor the price, and this deal never happened. But the immediate impact was that the dealership took down the chatbot to prevent further exploitation, which means the customer service was affected, causing reputation damage to this dealership. Then you have inference data. Inference data, as I said on the previous slide, refers to the real-time interactions and logs generated when users are interacting with an LLM model. If this data is not properly secured, it can be leaked or exploited, which is what we saw in this security research published by the security researchers at this company named as Wiz. So Wiz security researchers, in their research, they discovered that DeepSeek had exposed over 1 million log lines, including sensitive inference data, and this leaked prompt history posed a severe privacy risk, as attackers could retrieve confidential queries submitted by users. So imagine whatever queries you were submitting to DeepSeek, all of those queries, if somebody has to see and reveal them online, it's such a severe privacy risk, right? Then you have prompt log storage attacks. Prompt log storage attacks are also a very important attack vector that hold a very high hack value for attackers. So LLM interactions are often logged for monitoring, debugging, and analytics. But if logs are insecurely stored, then they will become target for hackers. And an example of this would be, a speculative threat example of this would be many AI providers, they store chat logs for improving their responses. And if these chat logs were compromised, they could expose, if these logs were compromised, then they could expose not only some chat queries, but also they will expose user credentials, sensitive requests, and some confidential business insights. Then you have the external API vulnerabilities. So LLMs will often call external APIs to retrieve data, update records, or provide real-time responses. So these APIs, they can be compromised if they are insecure, and they can become an entry point for attackers to walk in. An example of this would be the ADV web framework, where in October 2024, the researchers, they introduced the ADV web, a framework that generates adversarial prompts to mislead the VLM powered web agents into executing unintended actions. So VLM powered agents, you can read about them on Google. They are agents that can interact with images and videos, and they form a part of LLM processing unit. So in this way, then your LLM processing unit becomes it is a threat for remote code execution and API exploit attacks. Then you have training data poisoning. Training data poisoning is another very important attack vector, using which the attackers can mess and damage your AI system, your deployed AI model. A real world example of this would be Microsoft's Tay chatbot incident in 2016. What happened? Microsoft launched this chatbot named as Tay. Tay is short for thinking about you. This chatbot was launched in 2016, and it was designed to learn from user interactions on Twitter. The goal for launching this chatbot by Microsoft was to create a bot that would mimic human conversation and would adapt its responses over time. However, what happened was, within 16 hours of its launch, attackers, they started flooding Tay with harmful and offensive messages and tricking the AI then into absorbing and repeating hate speech. And since Tay's training data continuously updated based on user input, the chatbot started generating racist and inappropriate tweets. And Microsoft then had to shut down Tay within a day of its launch due to this training data poisoning attack. After the initial shutdown, Microsoft did try to relaunch Tay in a restricted mode the next day, but it quickly started to malfunction again. This time it began spamming a lot of users with these tweets like, you are too fast, please take a rest. And this appeared to be a looped response. So this indicated another failure, likely due to an internal error or another exploit. So this was a very interesting example for me when I was doing my research of how training data poisoning attacks can mess your model. If your AI model's training data sets are going to be by design dependent on user interactions, then you should be very careful. You should not accept any user input blindly into your AI model. You should put some safety measures in place, like content moderation. If I have to simplify this for you, then think of this like raising a child. When you are bringing up a child, you have this certain list of words that you don't say in front of a child, right? Hate speech, racist words, you don't use it in front of the child, because the child will pick up those words and start using them back. So in the same way, think of your AI model as a child and implement these safeguard measures like content moderation, rate limiting, reinforcement learning with some human oversight, human supervision. Don't let your AI model learn blindly from user input without any guards. Then to wrap things up, I would like to say that the bigger the attack surface, the bigger the risk. A large attack surface gives attackers more opportunities to find vulnerabilities and exploit them. A smaller attack surface is harder to breach because there are fewer weak points, and LLMs have a massive attack surface because of their complex architecture, numerous integrations, and exposure to public-facing APIs. So you should conduct a thorough assessment of your large language model system to determine which components really require public exposure and which do not, and then ensure that any exposure is minimized and limited to what is necessary. And if certain components such as training data require exposure, then do implement some content filters. So this then concludes our discussion for the LLM attack surface. If you have found this video insightful, then check out some of my other cybersecurity videos in my playlist. I believe you can only secure what you understand. So you will learn from these videos about AI systems, what they are, and only once you have a good understanding of what an AI system is, you will be able to secure it better. Alright then, thanks for your time. I will see you in the next one.